So we proceed with the afternoon New York Times session of our conference. So as Socrates said, algebraic geometers are like Greeks. They are attracted to the scenes, to the Hodge theory. So I'm paraphrasing. And one of the reasons, actually probably the main reason for this attraction is, of course, Philip Griffiths. So the man who turned to gold everything he touched. Of course, he got quite a bit of awards and prizes for that. I mean, he was definitely, he is a member of National Academy of Sciences, of Russian Academy of Sciences, he received the Wolf Prize, Chern Medal, and many other awards. And we are very happy to have the total and global teacher of a generation, algebraic geometers, Philip Griffiths. Philip?
Thank you, Ludmil. And the talk today will be on completions of period mappings. There's the outline. Yeah. I will begin with an introduction first to just set some notations. B bar comma Z is going to be a pair. Many of the applications are to moduli, so formulating things in terms of pairs is quite natural. Smooth, projective variety, and a normal crossing, reduced normal crossing divisor. The data phi is given by equivalently either by a period mapping or by a variation of polarized Hodge structure over B, the open quasi-projective variety gotten by taking out the normal crossing divisor Z. The objective today is to discuss some natural completions of the period mapping, extending it to the compactified projective variety B bar mapping to something. So informally stated, two of the results are that there are two natural completions, a maximal one and a minimal one. The minimal one is analogous to a Satake-Bailey-Borel in the classical case when you have a Hermitian symmetric domain and an arithmetic group. The former is in some way analogous to toroidal compactifications, and it gives what might be a candidate for a general definition of a toroidal completion of the image of a period mapping. I should emphasize here that we're mainly interested in the case when D, the non-classical case, when D is not Hermitian symmetric. So among the applications of these completions are properties of line bundles on the data. There are many results, both classical and recent, concerning neftness and bigness of such line bundles. Somewhat more subtle are issues of freeness or ampleness. And part of the objective of what we were doing was to understand what is needed to refine the results from neftness and bigness to freeness and ampleness. So informally stated, if you have a generic local, one result is if you have a generic local Torelli, then for sufficiently small epsilon, this Q line bundle is free. And if local Torelli holds, then without the epsilon, it is free. And there are necessary and sufficient geometric conditions that it be ample. These are expressed in terms of a Gauss map which turns up very naturally when one tries to understand the geometry, global geometry at infinity in the data. Another type of application that I have very little time to discuss today is to the boundary structure of moduli, especially of general type varieties. The Kolar, Shepard-Barron, Alexiev moduli space exists, and one is interested in understanding what is the boundary structure. There are very few examples of this, and that was one of the motivations for this work, was to understand some simple examples of the boundary of the KSBA completions of moduli of general type surfaces. One point to emphasize is that these constructions are relative. Given the data, you produce a completion. This is in contrast to the classical case where one is mapping to a quotient of a bounded symmetric domain by an arithmetic group, and you construct various completions of that and try to extend a period mapping. Here, the actual completion that's constructed depends on the initial data. The global study of period mappings on the open is a long-standing subject. Typical types of results are that B comma Z bar is of log general type. It should be B bar comma Z bar. That omega 1 of B bar log Z is Neff and big, and hyperbolicity properties of B. These proofs of these results are derived from the global geometry on the open variety B, together with the local geometry on the divisor at infinity Z, especially using the Catani-Kaplan-Schmidt analysis of what locally the Hodge structures look like when they degenerate. Okay. It became apparent in thinking about the moduli questions that one really needs global understanding of the geometry at infinity of the period mapping. And that was what motivated the construction of these completions. There's some recent work that's referred to here. There's a bibliography at the end of these nodes that have some techniques that are related to some of these discussed below. I'll mention more about that later. To establish the preliminaries and notation, a variation of Hodge structure is given by a holomorphic bundle with integrable Gauss-Menin connection. The kernel, the horizontal sections, are a local system which we assume is the complexification of one that's defined over Z. The holomorphic bundle has a holomorphic filtration, Hodge filtration, satisfying the differential relation. Throughout, we assume the existence of a bilinear form. We want polarized Hodge structures for the variation of Hodge structure for the period mappings. All the Hodge structures and then the mixed Hodge structures will be polarized. As usual, without essential loss of generality, we can assume that the monodromy around the irreducible components of the divisor at infinity is unipotent. And then there are canonical Deligne extensions of the Gauss-Menin connection. Dualizing, you get a bundle map to the F inverse, the -1 part of the Hodge filtration on the endomorphisms. It's convenient here to use Carlos Higgs formalism, passing to the associated graded, and then the differential of the period mapping is given by this a map in equation 2.1. In the period mapping formulation, we are given a vector space, a lattice really, in a bilinear form, and you look at the set with given Hodge numbers, we denote by D the set of polarized Hodge structures given by filtrations on the complexified vector space, which together with the bilinear form define a polarized Hodge structure of weight n. This gives you a homogeneous complex manifold that's an orbit in the compact dual, and the completions that we'll discuss will, of course, be related to what goes on with the orbit structure on the compact dual. So upon giving a reference point in the open variety, giving the variation of Hodge structure is equivalent to giving the period mapping, where the group gamma we're going to take today to be the monodromy group, not an arithmetic group. Okay. Using the period domain formulation allows one to apply Lie theory to the variation of Hodge structure, and that will be the crucial ingredient in the main structure theorem I'll state later on. A mixed Hodge structure is given by a triple vector space and two filtrations, a weight filtration W, increasing defined on the rational vector space, and a Hodge filtration defined on the complexification of the vector space, with the property that on the associated graded, the induced filtrations by the Hodge filtration give Hodge structures, usual definition of a mixed Hodge structure. The set of mixed Hodge structures with fixed associated graded will be denoted by E. E has a structure, namely they're maps where the EKs are K-fold extensions in E. So E1 is the set of extensions of one Hodge structure of the associated graded by another. E2 consists of those together with a pair of extensions that are of length 2, as indicated there. And you can sort of picture that there's an increasing sequence where we consider all K-fold iterated extensions of mixed Hodge structures. The first one is an X1. It's a compact complex torus, and the tangent space is a Hodge structure of weight -1, whose kth summand is, so the X1 is a direct sum over the associated gradeds of the mixed Hodge structure. And the kth summand, the tangent space, has a Hodge decomposition as indicated here. The important part will be the part over the brackets. Okay. The higher extensions fiber-wise, the higher extensions fiber successively, and the fibers are they're extensions of compact complex tori by a product of C stars and Cs. I should have mentioned that. The tangent space itself is a Hodge structure of weight -L that for L bigger than or equal to 2 has no summands that are close to the middle, if you like, in a Hodge decomposition. Among mixed Hodge structures, there's a special class arising from the logarithms of monodromy. So given a nilpotent endomorphism, there's a unique weight filtration as indicated here, drops the weights by 2 and satisfies a hard Lefschetz property. A limiting mixed Hodge structure is in a mixed Hodge structure whose weight filtration is given by such an N, and which acting on the Hodge filtration drops it by 1, decreases it by 1. More generally, if you're given commuting nilpotents, then you can have a monodromy cone, and such that the ends in the interior give limiting mixed Hodge structures. These limiting mixed Hodge structures are the gradeds are polarized. The polarization depends on the end. The extension data associated to a limiting mixed Hodge structure, it has some geometric property that's only partially present for general graded polarized mixed Hodge structures. And the part we're interested in today, the most interesting part for this talk, is if you look at the dual cone to the monodromy cone, then for each element in the dual cone, there's a line bundle over the level 1 extension data. Okay, so you have not only for the level 1 extension data, a compact complex torus, but from the limiting mixed Hodge structure property, you have a bunch of line bundles. So the basic results are, I'll go over those briefly. Given the original data, it's known from Catani, Kaplan, Schmidt that to each point in B bar, there's an associated and equivalence class of limiting mixed Hodge structures. Inside B, we just take the usual polarized Hodge structure. On the boundary, the limiting mixed Hodge structures are parameterized by the monodromy cone, and there's an equivalence relation, which is the one you would expect that really corresponds to action of monodromy. These mixed Hodge structures are taking place on a fixed vector space. Those vector spaces can only be identified by monodromy. And the monodromy, there's a global aspect where you go out into B. We're going to be primarily concerned with the local aspect where the monodromy is around the strata in the divisor at infinity. So the first definition, the maximal extension, simply assigns to the original data, the B bar, comma, Z, comma, phi, the set of equivalence classes of limiting mixed Hodge structures. Okay. Our conjecture is that this is itself a projective algebraic variety. That's not proved yet. What can be shown is that it has a well-defined, what would be the normalization if it were a variety, and that is itself a compact, complex analytic variety. Okay. So the image of the maximal extension is supposed to be a projective variety. You can get something, but not the whole statement so far. It retains the maximal amount of Hodge theoretic information in the original data when you go to infinity. Okay. At the other extreme, what one does is look at these limiting mixed Hodge structures that occur at infinity, the image is P bar sub upper T, and take the associated graded polarized Hodge structures. So more precisely, over the strata at infinity, the Zi star is just the intersection of a bunch of these Zi's, the smooth part of that. And you have period mappings gotten by taking the associated graded to the limiting mixed Hodge structures. And taking the union over these, that defines the other extension of the original period mapping, which is supposed to be the analog of Satake, Bailey, Burrell. So instead of taking the full limiting mixed Hodge structure, you throw out the extension data. That's what you do in Satake, Bailey, Burrell. Over this P bar sub S, there is a natural line bundle, and that's conjectured to be ample. In the classical case, this line bundle is the one arising from automorphic forms, and it's proven by Bailey-Burrell that it is ample. It's proved in a few special cases in the non-classical case, but is not known in general. What is known is that it's ample over B, or the image of B. This just P in the original notation. This is what was recently proved using O minimality and to construct an analytic structure on the image of the period mapping on the open B, and to then show that this line bundle is ample there. Very beautiful, very interesting work. The basic idea behind the study of the period mapping at infinity is this, that if you restrict the period mapping to the divisor at infinity, it gives you a diagram as indicated here. The composed mapping that you map the divisor at infinity to this P bar T, that's the set of equivalence classes of limiting mixed Hodge structures. Then you throw away the extension data and map down to P bar S. That composition is like an ordinary period mapping on Z, right? You're gonna just polarized Hodge structures. But there are two major differences from an ordinary period mapping. One is that on the fibers, there is non-trivial Hodge theoretic information given by the variation of the extension data on the fibers. So the associated graded is fixed. The extension data will itself be varying. So that's geometric information along the fiber. Okay. The second is that there's non-trivial Hodge theoretic information given by the variation of the extension of this extension data. And that's the key point. So I'm going to explain this in detail below, but essentially what it does is relate the variation of the extension data along the fiber to the normal co-normal bundle to the fiber in B bar. Okay. So it's the information along the fiber relates to information normal to the fiber. So for the next step, one introduces sets that are intermediate between the two extremes, the two full limiting mixed Hodge structures at the top, the associated gradeds at the bottom, and you look at the extensions up to certain levels, as was discussed earlier. That gives sort of set theoretic tower of maps like this. These are maps of sets, not of varieties. And on the other hand, to study the period mapping at infinity, it's useful to decompose it according to this diagram on the previous page. We'll let f of phi k be a typical fiber of the kth mapping. The first result that's known is that the fiber of the mapping to what would be the Satake-Bailey-Burrell, the P bar sub B, P upper bar B, those fibers are compact subvarieties. That's really based on the Catani-Kaplan-Schmidt results. So to say what the fibers of the higher ones are, I'm going to assume that the fiber of phi naught, the first one, is irreducible. You don't need that, but it makes it simpler to explain. And then the structure theorem is that, so it's irreducible, but it's only defined in a Zariski open on these strata, right? Because you're looking where the associated graded to the limiting mixed Hodge structures form just an ordinary family of Hodge structures. They don't decompose further. That means you shouldn't be hitting lower dimensional strata. The first result is that the first mapping, phi1, that maps you to the level 1 extension data, that's this compact complex torus J, that extends across the strata. So it extends to the whole complete variety. Okay. So what we're saying is that even though the Hodge structures degenerate, the level 1 extension data does not. Okay. That's really a special case of a general result about holomorphic maps from a Zariski open set of an irreducible variety to a compact complex torus. Such maps extend to the complete variety. That's an argument using the mixed Hodge structure, mixed Hodge structures on the data involved. So going back to the result, the second part says that the image lies in a translate of an abelian subvariety. You have this compact complex torus, all right, and in it you have a bunch of line bundles over it, and the image lies in the part in that diagram that I gave for the tangent spaces, the Hodge structures of type -1, 0, plus 0, -1, the stuff right next to the middle. And moreover, if you're in the dual of the cone, the monodromy cone, you get a positive line bundle on the image. So what is happening is that the level 1 extension data is mapping to abelian varieties, and the positive line bundles are being parameterized by the dual of the monodromy cone. Then the main result and the main formula is that if you pull back one of these line bundles under the map given by the level 1 extension data, that is expressed in terms of the normal bundles to the components of the divisor at infinity with coefficients that depend on the pairing of the dual cone with the monodromy cone itself, restricted to the fiber. Okay. So what you've got here on the left is information along the fiber. It's the pullback of the level 1 extension data of an ample line bundle. What you've got on the right is information normal to the fiber. Okay. That's the key point in the global analysis that we've been able to do so far of the period mapping at infinity. So to get a feeling for this formula, the fiber will lie, a Zariski open will lie in one particular strata, smallest strata. All right, its closure may meet some of the lower dimensional strata. And suppose that doesn't happen. Suppose you don't meet any of the lower dimensional strata. Then if the level 1 extension data mapping is finite to 1, then the normal bundle is restricted to that fiber is a negative line bundle. This is the sort of thing you would hope for, because what you want is that the mapping from the full toroidal type object down to the Zataki-Bailey-Burrell object, that is going to contract a bunch of stuff. It's going to contract the analytic varieties where the associated graded to the limiting mixed Hodge structure doesn't move. So you would hope that some normal bundles would be negative. That's what's suggested by this formula. At the other extreme, suppose that in the fiber that normal bundle is trivial. That can happen if you have a sort of fibration picture. Okay, and then as Q line bundles, then the normal bundle is just trivial. going back to the formula, what happens in this formula is that the terms where the fiber is in the of the open part, where if you're in the Zariski open part of the fiber, which doesn't meet the lower dimensional strata, where the associated gradients don't degenerate anymore, then you get a negativity statement of the normal bundle. On the other hand, when you hit these lower dimensional strata, you get a positivity statement, okay? So there are opposite signs occurring in this formula, and it's the interplay between these signs that's the most subtle feature, not yet understood, about what the global behavior of this period mapping at the infinity is going to look like. Turning to the higher level extension data, the level 2 extension data maps a fiber of the level 1 extension data to a product of C stars. Okay, it doesn't go to anything compact, it goes to a product of C stars. That again, if you go back to what the tangent space to a fiber looks like, it has a Hodge structure, but in that Hodge structure, there's no pieces in the Hodge decomposition that are close to the middle. So there's no place that you could actually get something compact occurring. Okay. So this is just explaining that. And then a final use of this infinitesimal period relation is that once you get up to level 3, the fibers are finite. It's kind of interesting that you can say, okay, along these fibers, you have these iterated extensions. We talked about the first level that maps to an abelian variety. We talked about the second level that maps to a product of C stars. It stops after that. Only finite stuff appears. The nature of that finite stuff is quite interesting, and I'll come back to that. But this is a non-classical phenomenon. In a classical case, the only levels are 1 and 2. Everything stops there. Only in the non-classical case do you go to higher levels. So what is this finite extra data? What it is, if you write it out, it's periods of intervals that are sort of polylogarithmic type. These constants I mentioned, those resemble those that arise in these expressions for multi-zeta functions. And if you think about it, that's not so surprising, because imagine at one extreme that you have a variation of mixed Hodge structure of purely Hodge-Tate type. The sort of thing that has been much studied in recent years and has sort of beautiful arithmetic aspects to it. When you do that, the extension data that turns up can be at all levels, and the expressions for what that extension data is are given by multi-zeta functions. So the fact that you get iterated integrals, which then give multi-zeta function, is not so surprising. I think what is interesting is that in the geometric case, the one we're interested in, the geometric interpretation of what these higher level extension data constants will be is not understood. It hasn't been studied. Are they some sort of regulators of types that maybe they're even classical, I don't know, but it's not yet been looked into. And this is just summarizing what I said a minute ago. So for some applications, there are 2 types that I'll discuss. For the first, it's one of the freeness and ampleness properties of line bundles that are associated to this initial data. If you think about line bundles over complete varieties, smooth complete varieties. They're sort of roughly the properties such line bundles can break up roughly into these two groups. The Neff and big properties, those are numerical. The free or ampleness properties, those in some way are, if you like, geometric. And what has happened classically is that for the data that arise from a period mapping on the quasi-projective variety B, together with knowing the Catani-Kaplan-Schmidt asymptotic analysis locally at infinity, you can get Neff and big properties of various bundles. There's a long and very nice story here, very classical, some of it, a lot of it done by people who were interested in the Yataka conjecture some years ago, people who are interested in various hyperbolicity properties of moduli spaces, things like that. There's an extensive literature that's given at the end of this of these slides. Okay. Typical results are that the canonical bundle of B bar is log general type. The omega 1, the cotangent, the logarithmic cotangent bundle is big. And the Hodge line bundle is Neff and big. It's this last one that's used by Vive, Kolar, many people in the Yataka conjecture and things that grew out of that. Okay, they use the global geometry of the period mapping on B and the local analysis at infinity. So what can we use our understanding so far of the global nature of the period mapping at infinity to say about freeness and ampleness? I'm going to assume that these mappings at infinity on the open strata are fibrations. It just makes it easier to state the results. I think you need, they're probably not essential, but this hasn't been worked out. So the first property I want to discuss is a conjecture. We can only prove special cases. The main formula can reduce the conjecture to a combinatorial property of monodromy cones. The conjecture is assume you have generic local Torelli. That's that differential of the period mapping extended across infinity. That differential is generically injective. That's the thing that use the Higgs formalism that I put up in one of the earlier slides. Then there are rational, non-negative rational numbers such that this Q line bundle, the extended line bundle that was on the previous slide, minus a sum of components of the divisors at infinity with non-negative coefficients should be free. You can say, well, why not just having those coefficients all the same? And as will be explained, this cannot be done. You cannot make all the AIs the same number. It has to do with what I mentioned earlier, this geometric property of the variation of the extension data at infinity related to the normal bundle to these fibers at infinity. That has two types of summands with signs, opposite signs, and it's the interplay between the positivity and negativity that's going to force you not to be able to take all these coefficients to be the same. There are examples, easy examples that show that's the case. Okay. This is the result of Baker, Bruno Hobby, and Zimmerman that I mentioned earlier. The next property is, okay. There's an explanation in that of the combinatorial issue that arises. I think I won't go over this. It's in the notes, and the notes will be posted. The geometric nature of the combinatorial issue that arises really has to do with, I think, what in the classical Hermitian domain case is the construction of fans. It's a fan type property that one needs about the action of global monodromy on the monodromy cones that would give the result one wants if you have this property. The property can be expressed as a combinatorial one involving the effective cone of curves paired against these line bundles that turn up from the limiting mixed Hodge structure, the limiting mixed Hodge, the line bundles that turn up from limiting mixed Hodge structures over the level 1 extension data. And in the notes, I think I won't go over this here, there's an explanation of the first non-trivial case of this conjecture, and it explains by example why you cannot have both these coefficients equal. It's similar to the classical fact that if you have an isolated normal singularity on an algebraic surface, obtained by you take the resolution of that singularity, take an ample line bundle on the singular surface, and you want to say that the ample line bundle pulled back to the resolution of the singularity minus some linear combination of the curves that are contracted by the resolution minus some linear combination of those curves should be ample. That's true, but the linear combination of the curves you take must have different coefficients. They cannot all be the same. That reflects the nature of the singularity that was resolved. And it's something similar going on, I think, here, but it's not really understood yet. The next result is that the KB bar plus Z is Neff, and for rational epsilon sufficiently small, this line bundle is free. So one is able to get a freeness result. The stronger result should be that KS bar plus Z itself is free. We've not been able to prove that. One can ask, well, if this line bundle is free, is it ample? And here, if you take a toroidal compactification of an arithmetic quotient of a bounded domain, then you have Satake, Bailey, Borel. You can ask, what does this all boil down to in that case? In that case, this line bundle KB bar plus C is the pullback of the automorphic form line bundle on Satake, Bailey, Borel. It's the old result of Mumford. So it's not ample. It's free, but not ample. Okay. So you can say, okay, what are conditions that would make it ample? If you recall the level 1 extension data, you have a morphism from the fibers of the map that associates, that just the map to Satake, Bailey, Borel type thing. You just take the associated graded. You have a map to an abelian variety. Assume that this mapping is an immersion and look at the associated Gauss mapping. Then if you assume local Torelli in the form that this differential is injective, the thing that was in one of the earlier slides, then this line bundle is free always, but it's ample if and only if this Gauss map is an immersion. So that's sort of giving you some feeling for what the global geometry of the period mapping at infinity may look like. You're mapping the fibers of the mapping to Satake Bailey-Burrell to abelian varieties, and it's the nature of those mappings that I think really is the central part of the story. This result is, there's an sort of interesting aspect to it. If you take just classically the Hodge line bundle on B, assuming local Torelli, so that B maps locally one-to-one to a D mod gamma, you have a complete Kähler metric there. And it's known the holomorphic sectional curvatures are negative bounded below, from above, and the holomorphic bisectional curvatures are less or equal to 0 and strictly negative on open sets. So what that means is that you get a volume form associated to the Chern form of the Hodge line bundle on the open B. And you can look at its Ricci form. The Ricci form is strictly positive on B. Okay. So the proof of this theorem, though, is dealing not with B, it's dealing with B bar. The Ricci forms have to do with the Chern form and the canonical bundle. And you can say, okay, on B bar, you got singularities at infinity. How can you control those singularities? Well, Catani, Kaplan, Schmidt control the singularities of the Hodge bundles, but these are not Hodge bundles. The Hodge bundle, the Chern form of the Hodge bundle gives a Kähler metric, and it's the Ricci form of that Kähler metric. So it's second derivatives, if you like, of the period mapping coming in at infinity that you have to control. So that's the key analytical fact behind this result there. The freeness of KB bar plus Z. And there it's interesting that because of the local Torelli assumption, this logarithmic tangent bundle at infinity is a subbundle of Hodge bundles. Anytime you have a holomorphic bundle, subbundle of a holomorphic bundle, you have, and the larger bundle has a metric in it, the Hodge metric. There you have singularities at infinity, but those are controlled, as I said, by Catani, Kaplan, Schmidt type analysis. You have additionally, though, the second fundamental form that tells you how the subbundle is twisting in the bigger bundle. Okay, that's not Hodge theoretic. That's differential geometric. And the key to the argument in the theorem I mentioned is controlling that twisting, if you like, of the subbundle. So to close, I'd like to say just a little bit about the original motivation of mapping to moduli spaces. For algebraic curves, of course, a very beautiful, classical, much studied story, mg bar maps to its image in P and gamma, or mg in P and gamma, D by gamma. And there are various toroidal compactifications. The main one of when you're mapping mg bar seems to be the second Voronoi toroidal compactification, proved by Namakawa and Mumford that the map mg bar to this toroidal compactification extends. Okay, and it's not one-to-one, but one knows a lot about the extent to which it fails to be one-to-one. It's one-to-one along irreducible nodal curves, stable curves that are irreducible. So it's the combinatorics when you get reducible curves that create the situation that the mapping from mg bar into this toroidal thing is not globally one-to-one, but one understands the nature of the fibers, at least from a combinatorial description, quite well. One might ask, well, the extension of the period mapping that is in the main theorem that I'm talking about, how does that relate to this? And it's a reasonable supposition is that it actually agrees with what you got classically. Sort of what else could it be? But this has not been checked. When you come to higher dimensions, though, for example, smooth algebraic surfaces, the situation is very different. The analog of mg bar, I'll call it mx bar, where x is sort of a typical general type surface. Even if mx itself is smooth, there's some nice examples where this is the case, the mx bar will be highly singular at infinity. In fact, it has to be singular. If mx is smooth, and if you have a degeneration of a surface that acquires an elliptic singularity, an isolated elliptic singularity, so a normal degeneration, that has to be a singular point of moduli, of the completed moduli space. So in fact, you get quite singular behavior along the boundary of moduli. And one can say, okay, are there ways of at least partially desingularizing that? I should mention that a very nice study of the Kolar, Shepard-Bear, and Alexiev completed moduli space is the one by Franciosi, Pardini, Rolinski in a series of papers. They took the sort of first case, regular surfaces with kx squared equal 1, PG is 2, moduli space has dimension 28. You have a Torelli theorem. The image, by the way, of the Torelli mapping is a contact submanifold. The differential constraint on the period mapping is a contact structure, and you get a contact submanifold. And what I just mentioned, that for normal Gorenstein limit surfaces corresponding to the boundary points, these are singular points. For example, the surfaces with an elliptic singularity of degree 2, these are well understood, that has dimension 20 in a 28-dimensional space. Okay. So what is going on is that when you look at the extension data and the limiting mixed Hodge structure, that seems to be helping you desingularize the boundary point. So let's think about a degree 2 elliptic singularity. How are you going to desingularize the boundary point? You want to do a semi-stable reduction. It's classical that for a surface with an elliptic singularity, to do semi-stable reduction, you think of this elliptic, on the desingularized surface, you have an elliptic curve. Think of it as a cubic in the plane. Take the union of these desingularized surface, the one with the elliptic singularity desingularized, together with the cubic in the plane blown up at a certain number of points, and glue them. Glue them and blow up the cubic curve at a certain number of points. You get a del Pezzo. The number of points you have to blow up depends on the degree. And if you think of degree 2 and work out the numbers, you would expect you have to blow up 7 points. That's exactly degree 2. Okay. So what's going on here, at least in this example, is that looking at the image of this extended period mapping, the maximal one at a general point of the boundary for the FPR moduli completions, you desingularize by taking the limiting mixed Hodge structure. So we don't know how general this phenomena is. It's very nice in their examples. And sort of geometrically, though, it does make sense that in the limit, you've got too much information crammed into the Satake-Bailey-Burrell thing because you threw out the extension data, which you don't do for curves. Here, when you go to MG bar, you don't do that for curves. Here, when you go to MI bar, you do throw out the extension data at infinity. And if you put that back in, that at least is a realistic way to try to at least partially desingularize these moduli spaces. Okay, I put in the appendix some of the details on what I just said, but I think I won't go through that. I'll just stop here. Thank you.
Thank you, Philip. Any questions?
I had a question.
Yeah.
Could you give some idea for why you don't try to compactify the entire D mod gamma in the way you do for the case? You only compactify the image of period map.
It has to do with the differential constraint that if you try to do what Satake-Bailey-Burrell did, from a Lie theoretic point of view, nothing works once you get to the non-classical case. You can say, okay, let's just try to partially compactify it in the directions where you keep the differential constraint, okay? So we'll add in only those points that you think you have to add in from a Hodge theoretic point of view. This is what is a work which is carried out to some extent in the Kato-Usui partial compactification of these D by gammas. They assume that the gamma is arithmetic and make some other assumptions, and they have a partial compactification in that case. They also how it relates to the construction that we did, which is a relative one. We've not looked into that. I think there has to be a relation. We don't know what it is. I think we don't want to make the assumption that gamma is arithmetic, because there are now these, in fact, quite a few examples where gamma is a thin matrix group. So it's not a finite index in an arithmetic group. And that is going to cause a lot of trouble also when you try to do the Burrell-Bailey type stuff, or even the Kato-Usui type of analysis, because they need to use Siegel sets or fundamental domains for the arithmetic group. And those just will not exist for these thin matrix groups. So, you know, I think some years ago, Katani and Kaplan and a number of people tried to extend the Burrell-Bailey. They came across these issues and tried to extend them in the horizontal directions. The best work that has been done, the most complete analysis of that is, as I say, the Kato-Usui construction. But it does assume that gamma is arithmetic. So just how it relates to this one that we've been working on, we've not yet, looked into that.
Other questions? So Philip,
yes,
these conjectures about combinatorial expressions of the monodromy, are they for surfaces or they are general conjectures?
So far only for surfaces. We haven't thought about it in higher dimensions. for surfaces, you're really dealing with Hodge structures of weight 2, and they have some simpler features than general ones do. So the answer to your question is we haven't really thought about it.
Also, in your talk, you mentioned nodes. So these are the nodes, the one that you are going to. So when you say nodes, these are the nodes, what you have presented.
Yeah. So
how does one get them?
I guess these will be posted on the,
okay.
on the website for IMSA. So.
Okay, very good. Other questions?
Well, can I ask, if you take the potential toroidal compactification, is there expected to be some kind of deformation and obstruction theory thing with a Kuranishi space to tell the local singularities?
There will be. I think, we've not thought about that. The whole sort of deformation theoretic picture, the usual cotangent complexes, the X1, omega 1 OX and things like that. We've not really thought about how that fits into this.
I mean, that's not going to tell you too much about the Satake type compactification, right?
Yeah.
But you might expect that on the other one that might, on the bigger one.
Other questions?
Yeah. Hi, Philip. So I just, I guess a small comment that I don't think that Kato no Sui really require arithmeticity of gamma. They require neatness of gamma, which of course you can get around by passing to a finite cover. And I would also say the Bakker-Brunebarb-Zimmermann says on the surface of it that you need arithmeticity, but you can also get around that because the infinite to one map from the D by the monodromy gamma to D by an arithmetic gamma containing it, well, that could be infinity to one. The actual period mapping image will be finite to one on that by your properness result. And so then you get something that is algebraic in the image that has a finite cover, which is therefore algebraic. So I don't think it's that the gamma being arithmetic really shows up as a strong constraint in those other things.
Yeah, that's a good point. I understand. You're not going to be able, though, to do Siegel sets.
Right, right.
And stuff like that. I think that to me was always where I sort of philosophically got stuck. It's probably too old-fashioned to be stuck on Siegel sets, but they were, that's where, that's my first memory of this stuff, and I've not been able to outgrow it.
Thanks. Beautiful talk.
All right, other questions? If not, let's thank Philip. And so we will proceed at 3:30 New York time. Thank you, Philip, again.